Welcome to the second lesson in Chapter 4 Sequences and Series, Year 2 Pure Mathematics. Today we're going to have a look at proving something very exciting result, one of my favourite results in fact. Prove and apply the formula for the sum of the first n terms of an arithmetic series. Now notice we've used the word series here. There'll be more about that later. So let's just get straight into it. There's some preparation work if you want to refer to your year one work or your pre-GCSE work that was in the transition booklet. But if you're ready to go, please have a go at have a go at the warm-up questions and pause the video, and then I will go through the solutions with you. All right, so let's have a look at question 1 in the warm-up. So what are we asked to do here? Now, this is actually a question that came up in the examples in the previous lesson. So we're asked to find the first, or we're told the first, second, and third terms of an arithmetic sequence. And if we just have a look at these terms, they're all given in terms, so terms in terms of, which is confusing. But the first term has an unknown, a k value, as does the second and the third terms of this sequence. So it's a good idea. I'm just going to, well, we're a bit stuck for space here. I'm trying to cram in quite a lot into this space. So we know this is the first term of our sequence. This is the second term, and this is the third term. And we need to determine the value of k. Now, we saw a strategy for this in the previous lesson. We know because this is an arithmetic sequence, you know, these words, this language is not throwaway. It tells us important properties about the sequence. So because this is an arithmetic sequence, we know that there is a common difference, d, between each of these terms. So we're adding d each time. Now, a quick way of doing this, because we've established it in the previous lesson, is to take the differences between consecutive terms. So just as a shorthand, if I take term number 3 and subtract term number 2, that will give me the common difference, right? That this is essentially equal to the common difference, okay? But likewise, if I subtract term 1 from term 2, this also would give me the common difference, because common being it's present, or it's common to all terms. So we have an equation we can set up here. So let's do it. So if I take term number 3, which is 10k, and then I subtract the second term, and I've got to be careful here, I'm subtracting the whole of the second term. So I'm going to use brackets, parentheses if you like. That must be the same as taking the second term and subtracting, I've run out of space, which is annoying, subtracting the first term. Oops. 3k subtract 2. Okay, now this will give me an equation that I can solve. So let's just multiply out these brackets by -1. So therefore, 10k subtract 5k subtract 2 must be equal to 5k add 2 subtract 3k, and be very careful here, add 2, because we have the double negative. All right, now let's collect all the k's together. So I'm just going to highlight those. So we have 10k subtract 5k, that's all right. And then we have 5k on this side and -3k on this side. So just collecting all those together. So 5k and then subtract 5k, so that's going to cancel. And then that's going to give us 3k on this side. Okay, so I'll just go through that again in case that wasn't clear. The 10k subtract 5k on the left will give me 5k. I have 5k on both sides then, they're going to cancel out. So then if I add 3k to both sides, hence that's why I get the 3k on the left. And then on the right-hand side, I've got plus 2, which is 4. And then I can add another 2 to that, so that's 6. So to answer the question, k is equal to 2, since 3k equals 6. So we've got the value of k, and then we're asked to write down the first 5 terms of the sequence. Okay, well, term number 1, let's write that out again, is going to be 3k subtract 2. So 3 multiplied by my k, which is 2. Let's do that in blue. So 3k subtract 2. So that's 6 subtract 2, which is 4. Okay, so that's given me the first term. Now I'm going to need the second term to establish what the common difference is. I think it'd be quicker than substituting into either the left or the right of the equation I set up earlier. So the second term is going to be 5 times k, so 5 multiplied by 2. And then I've got to add 2 to that. Okay, so that's going to give me 12. So now I can establish what the common difference is going to be. And again, you don't have to do it this way. There's lots of ways of doing this. So my common difference is, of course, going to be 8. So now I can write down my sequence. So I now know from the work I've done, my first term is 4. My common difference is 8. So let's write down the sequence now. So it's going to be, oops. So we're going to have 4. 4 plus 8 is 12, which we've already established. Add 8 to that, which is 20. Add another 8. And I need one more term. That's going to give me 36. And then there'll be more to come. Okay, so there's my first 5 terms. Now, it asks for the nth term rule of the sequence. Well, like we've written out the first 5 terms. We've got the A, we've got the D. Let's use the formula. So UN is, of course, A added to N subtract 1 multiplied by D. Let's just write down what our A and our D are. A is obviously 4. And D is going to equal 8. And we will substitute those into the formula. So my UN is going to be 4 added to N subtract 1 multiplying my common difference 8. So this is going to be 4 added to 8 multiplying N subtract 1. Expand the brackets. 4 added to 8. N, 8 times N, 8N. Subtract 8. Okay, and then we're going to have 8N. And then 4 subtract 8 is, of course, negative 4. So we have 8N subtract 4 for our nth term rule. And as you can see, that because the sequence differs by 8, the common difference is 8. This means it's a shift in the 8 times table. So it's the 8 times table with 4 removed in each term. Okay, great. So in question 2, it says, using the sequence generated in your answer, let's remove that, to question 1, part A. Okay, so we've got our sequence, yes. We're going to add, up some partial sums here. So we're going to add the first and the second term together, and then the first 3, and then the first 4, and the first 5. Okay, let's do that. So it's quite a simple task. It says, what do you notice at the bottom? All right, well, let's see if anything interesting is happening here. So if I add the first 2 terms, so that's simply going to just be 4 added to 12, which is, of course, 16. Okay. Okay, and then I add the first 3 terms. So this is going to be 4 added to 12, added to 20, So in other words, I add 20 to my previous sum, if you like. So that's going to be 36. Ooh, okay. And then I add the fourth term. Now, rather than writing it all out again, let's just use a little bit of common sense here. We've added the first three in the previous question, haven't we? So I know that sum there is, of course, equal to 36. So we know this is equal to 36. So I just need to add 36 and the fourth term, which is 28, together. Now, if you add 36 and 28 together, of course, you get 64. All right, okay. These answers do look interesting, don't they? So we have 64. And once again, we've just worked out the sum of the first four terms. So I know this sum here is, of course, 64. So all I need to do is add the last term that I've written out. So that was equal to 64. So I have to do 64 added to 36. Ah, right. Okay. Well, that's a nice number. Okay. What do you notice? Well, what do we notice? Well, if you know anything about square numbers, I think it's obvious, isn't it? These are all square numbers. Okay. So let's just make a note of that. So all sums are square numbers. Now, is there anything else we need to consider here? Is it just the fact that they're all square numbers, or is there another link? Very interesting. Well, we'll come back to that. I think we'll leave it at the square numbers. I think that's a nice, interesting result. Now, for question 3, we're asked to solve a quadratic equation. So we just need to rearrange this, make sure everything is in the form that's required. So we have 5n squared, add n, subtract 2000. And this is, of course, going to give us 0. Okay, I think we can use our calculators for this one. So let's just identify the coefficients. So quadratic equation, A is, of course, 5. B is equal to 1. And C is equal to negative 2000. So let's go to our calculators. I'll just move this text over a bit if I can. Let me. No. You just erase that. It'll be easy if I just write it over here. I should have put the calculator up first, but never mind. So I'll just rewrite the equation. So it was 5n squared. N subtract 2000 equals 0. And A is equal to 5, and then we've got the rest already. Okay. So on your class whiz, if we just select the menu, and if we go down to equation solver, which you've used this before, okay, we'll select that. Remember, a quadratic is a degree 2 polynomial, so we'll select polynomial degree 2. We talked about degrees, didn't we, in algebraic fractions, so degree 2, and then we input the coefficients. So A is, of course, 5. B is 1. And C is negative 2000. We'll press equals, equals again, and there we have our our roots, if you like. So the first one, we have x1. What our calculator gives us. So we'll give it to 3 significant figures. If it doesn't specify the accuracy in the answer, as you know from the exam specification, we give the answer to 3 significant figures if it doesn't specify otherwise. And our second solution, which is x2, so that's going to be negative 20. Negative 20.1 to 3 significant figures. All right, so those are the solutions. So in other words, the solutions to the equations, that's what was given on the calculator. We have 2 options. So either n is equal to 19.9 or n is equal to 20.1. So those are the answers to the equation. I would always indicate now that you've written down A, B, and C, just indicate that this was done on the class whiz. Okay, using the quadratic formula essentially. Okay, and let's move on to question 4. So we're asked to find the first and fourth terms of an arithmetic sequence. Oh, sorry, the first and fourth terms of an arithmetic sequence are given to us. So the first term is k subtract 4. Okay, and the fourth term is k squared. Now, this is really important, and we're also told k is greater than 0. Now then, so the first term, term 1, is k subtract 4. And the fourth term, k squared. I always just like to write this information down myself so it's clear in my head what I'm doing. And it says, given the common difference is 8, find the nth term rule for the sequence. Well, how do we do this? Well, if we know the first term and the fourth term, and we're told the common difference is 8, well, this goes back to something we talked about in the warm-up for the previous lesson. Now, if I just sort of rewrite what I've just talked about here, we have 4 terms essentially, 2 that we don't know and 2 that we do know. So the first term, let's write it in again. This is k subtract 4, and this is k squared. Now then, if we're told the common difference is 8, well, what this means is to get from k subtract 4 to the second term, I have to add 8. Okay, to get from the second term to the third term, I also have to add 8. These are arithmetic sequences, remember. It also states that in the question. And to get from the third term to the fourth term, I add another 8. Now, this is where we can set up our equation. It's all there. All the information's there. It's just knowing how to use it. So we know that k subtract 4 is my first term. And if I add 3 lots of 8, I know this will give me the fourth term, which is k squared. Right, now we have another quadratic to solve. So in other words, k subtract 4, and then 3 multiplied by 8 is 24, of course, equals k squared. Collect your like terms. So k add 20 is equal to k squared. Let's keep a positive k squared, and let's put everything else on the other side. So I'm going to subtract k and 20 from both sides. So it's going to be k squared, subtract k, subtract 20. Now, I don't think we'll need to use the class whiz this time for this. We should be able to factorize this. So 0 is equal to k. Now I have a negative k, so it looks like negative 5 multiplied by k, add 4. Okay, so to solve the equation, so that means that k is equal to 5 or k is equal to negative 4. Right. Let's go back to the information again. This is where, once you've solved your quadratic, it's a really good idea. Just reread the question and see what we're asked to do, because you can get carried away and just say, all right, I've solved the quadratic, I'm done. But in this kind of context, probably not. Now, it says here, k is greater than 0. So that means I can disregard this solution. So only k equals 5 is my solution. And now we have to find the nth term rule. So I'll make a note of this. Find the nth term rule. Well, if we know k is 5, I can now write down what each of my terms are going to be. Remember, I only need the common difference and the first term. So I know the common difference is 8. That was given to us in the question. So I just need to jot down what the first term is. So my first term is going to be k subtract 4, which is here. Okay, we wrote it down earlier. There's my first term. So I have to put that in here. Now, if we know k is 5, 5 subtract 4 is just going to be 1. So this is just going to be 1. Okay, and now we have the information. So we've got all the information now to find the nth term rule. So I'm going to use the formula now. So un is going to equal a plus n subtract 1 multiplied by the common difference, which is 8. So it's going to be 1 added to 8 multiplied by n subtract 1. In other words, it's 1 added to 8n, subtract 8, and then collect your like terms. So this is going to be 8n. And then 1 subtract 8 is, of course, negative 7. So we knew it was a shift in the 8 times table right at the beginning because it told us the common difference was 8. So we know it's some shift or translation of the 8 times table. So it's a shift of 7. Okay, and that concludes the warm-up. So in this lesson, we're going to consider what an arithmetic series is. Now, we've met an arithmetic sequence. It was, of course, just a linear sequence. And we've seen an example of a linear sequence here. So what is a series? Well, a series is just a sequence where the terms of the sequence are added. In other words, it's the sum. So it's the sum of a sequence. So this is what a series is. So the series correspondent to the sequence that we're given would be 5 add 7 add 9 add 11 add 13. So just finding out what that sum actually is. Now, before we start doing this, there's a particular way I'd like you to think about these sums. We are going to have to evaluate them, and they can get quite complicated and quite lengthy. But with the right approach, we can actually make it quite simple. So there's an investigation, and what I'd like you to do is to try parts 1, 2, and 3 of the investigation first. So have a think about it, try some ideas out, and pause the video, and then I'll go through these 3 investigations in a bit of detail. Okay, so have a go at that first, and then I'll go through it. Okay, so you've had a go at hopefully representing these sums as patterns. Now, if we look at the first investigation, we have the sum of 4 terms here. Okay, so we have 4 terms. That might be important. I'm just going to write that down. So we have 4 terms. And this calculation is represented in an unusual way on the right-hand side of that equation. So the question is, where have those numbers come from? And how do they relate to the diagram? Well, if we look at the diagram, notice that if we look at the first row, we have 2 stars. Okay? Sorry, beg your pardon, 2 dots. 2 dots in the first row. And then adjacent to the 2 dots, how many stars do we have? Those black stars. Well, if we look at the black stars and count them up, you'll notice that there are 11. Now, why is that significant? So there's 11 black stars. Well, if you go back over to the summation on the left, you'll be able to see that we have 2 is our first term. That's our A value for our sequence. Okay, so 2 is our first term and 11 is our final term. And you'll notice that if you add those 2 numbers together, you get 13. In fact, if you add up the middle 2 numbers, you will also get 13. Okay, so 5 add 8 is also 13. Now, where does that manifest in the diagram? Well, let's have a look at the second row. If we have a look at the second row, we have 5 red dots this time. Okay, oops. So that corresponds to the second term, which is 5. And we have, if we just highlight those, how many of those black stars do we have? Well, we have 8 of them because this is a rectangle. So if the length of the rectangle is 13 shapes and we have 5 taken up by red dots, then obviously there must be the difference is, of course, 8. So we can kind of deduce that without actually counting them. So this must be 8. And we know that 5 plus 8 is 13. So we've established that there are 13 shapes in each row. Now we have 4 rows on here, which kind of indicates why we have 4 lots of 13 in the numerator of that calculation, because there are four rows of shapes going down here. Now, why would we have 4 rows of shapes? Well, where does the 4 come from? Well, it looks like we have 4 terms. So we have 4 terms. So there's a link between the number of terms there. So the 4 terms, oops, that seems to perhaps this corresponds to the number 4 in the numerator there. And then the sum of the first and last term here and here seems to correspond to this number. And then why do we divide by 2? Well, if we actually carry out 4 multiplied by 13 on this diagram, you'll notice something quite interesting. Now, if we do 4 multiplied by 13 in that direction, okay, that's not the answer we're looking for, is it? That would give us 52. But remember, we only want to add up 2, add 5, add 11. Sorry, I beg your pardon, add 8, add 11. Now, if we add up all these, we're actually adding up twice the amount that we need. And you can see that because in the third row, we've got 8 red dots, and in the fourth row, we have 11 red dots. Okay, and if we just correspond that to the black stars, here we have 5 black stars and 2 black stars. So you'll notice if we look diagonally, we have the sequence 2, 5, 8, 11, which is what we're adding together. And in terms of black stars, we have 2, 5, 8, and 11. So if we do 4 multiplied by 13, we're actually adding up these terms twice, which we don't need to do. we're only considering half of the whole shape. So you can see it diagonally as well. If I just draw diagonally on here, I know it's getting a bit messy. Okay, so if I just separate out the red dots from the black stars like that, we'd only want half of the whole diagram. So how does this play out in investigation 2? Well, if you kind of saw that pattern and you could deduce what was going on. Now, without me drawing out all these shapes, if I was drawing out the pattern, I would say, okay, if I look at the first term and the last term of this series, that tells me that my diagram might have 4 red dots going along there. I'm just going to sort of simplify it just by using a line. And then I would need to have 19 black stars, which gives me a sum total of 23 shapes. So I would have 23 shapes in the first row. Now, to create the rectangle, I would also have to have 23 shapes in the second row. Now, I also know that I've got 4 terms again. So that means that there must be 4 rows of this. So my second row, I would have 9 red dots. And to make sure I get 23, 14 black stars. And in the third row, I would have 14 red dots and 9 black stars. And then in the final row, so it ends naturally, doesn't it? Okay, in the final row, I would have 19 red dots and 4 black stars. And that would give us the rectangle. All right, so to get the area of the rectangle, would simply, well, we've got 4 rows there, multiplied by the total number of shapes all the way across, which is 23. I'll just label that. So that will be 4 multiplied by 23, so 23 shapes and 4 lots of them. Okay, so we can put that in the calculation. So this would equal 4 multiplied by 23. But obviously, if I multiplied 4 and 23, I would have twice as much as what I need. So I'd have to divide that by 2. Okay, and that would, of course, give me 46. All right, so that's the way I'd kind of like you to think of this at the present time. Now, it says at the bottom in part 3, extend this idea to work out something else. So I'm just going to scroll down so we can see what part 3 is all about. I'll just do that, and then I'll just clear this. Okay. Now then, what have we established so far? Well, we seem to, if I want to do this quickly, okay, we know that we're going to need to add together, I should say, the first term and the last term. So they're really important. Okay, so we need to add these 2 numbers together. Remember, that gives us the length of the row. Okay, so it tells us how many shapes are in each row. So let's just make a note. So there would be 8 plus 98. Okay, and if you add those together, that's going to be 107. No, no, it's not. Undo. Sorry. 8, that's 106. So there'll be 106. That tells us the number of shapes in each row. First of all, and how many rows are there? This is the question. We need to know the number of rows. If you know how many shapes are in each row and you know how many rows there are, all you have to do is find the area of the rectangle which it would give, and then divide your answer by 2. But how many rows are there? Well, this is the question. This is where it's a bit tricky in this situation, because we don't actually know. We've been given some of the terms, but not all of them, because we have this plus ... situation. So we need to find out how many rows there are. Well, let's just do a bit of work here. We know the first term is 8, okay? And we can easily work out the common difference. Okay, so the common difference, how do I get from 8 to 13? Well, I must add 5. How do I get from 13 to 18? Well, I'm adding 5. So my common difference is, of course, 5. Okay, it's a series. We're adding the terms together, but it behaves like a sequence. You can think of the terms interchangeably in that respect. Now we know that. Okay, how does this help us? Well, let's have a look at the last term. If 98 is a term in my sequence and it's the last term, well, we can use that to our advantage. So we could say, okay, UN, I don't know which term it is, but I know it's equal to 98. So what's the value of n that will give us, i.e. which term in the sequence is it? What position is it in? Well, let's set up an equation. So we know that a plus n subtract 1 d will be equal to 98 in this instance. So let's sub everything in. So my a is 8. Okay. I don't know my n, but I do know my d. So I multiply it by my d, which is 5. And I know my answer is going to be 98. So I can solve for n. Okay, great. So let's subtract 8 from both sides and expand the bracket. So we have 5n subtract 5 would equal 90. In other words, add 5 to both sides, so 5n would equal 95. And therefore n would equal 19. Okay. So there we have it. So we know that in this series, we're starting off with the first term, the second term, the third term, and we're ending on the 19th term. Okay. Now, let's set up that calculation in a similar way to what we did in the first two investigations. So I've not got much room. I'm going to have to do this underneath. So in my investigation, I know that in the numerator, the number of terms I've got is 19, okay? I know that I'm multiplying it by the sum total of the first and the last terms, which is also the sum total of the number of shapes I have in each row. Okay, so it's that number there. Now I've already established that number, it's 106. Okay, so it's 106, so I'm going to write that in. It's 19 multiplied by, 106. And that will give me the area of the whole rectangle. Now that's just twice as much as what I need, so I need to divide the whole thing by 2. Okay, now we can actually work that out. Okay, so I can do the 106 divided by 2 first. Now that's quite easy. So I know that's 53. Now 53 times 19, the bit of preparation will give me 1007 for that answer. You can check that on your calculator. Okay, so what we've actually done there is in a kind of a roundabout sort of way, but we'll get onto the reason why we do it like this shortly. We've actually calculated the sum of 19 terms of an arithmetic sequence, okay, which we call a series, because that's what we call it when we're adding them together. Okay, so let's have a look at the sums of an arithmetic series. Now, I'm going to introduce you to a very famous mathematician, if you've not met him before. So this gentleman is Carl Friedrich Gauss. I hope I've pronounced his name reasonably well. I did do German GCSE, but that was 24 years ago since I'd done that. So Carl Friedrich Gauss, according to his, according to a chap called Wolfgang Sartorius von Walterhausen, he has some interesting anecdotes about Gauss. So he claims that when Gauss was 3 years old, or barely 3 years old, he managed to correct an error his father made. And the famous story, now this is a famous story, and I don't know if it's myth or not. It seems to have, it's been cited, but this was the famous story about Gauss, which is a classic way of leading into this idea. What he did was he solved an arithmetic series problem faster than anyone else in his class of 100 students. And I've even heard somewhere that he was given this task because he was being mischievous and his teacher wanted to sort of teach him a lesson and asked him to add up the sum of the first 100 numbers. And he solved it very, very quickly, much to the teacher's dismay. So we're going to have a look at how Gauss probably solved this problem. So I've just sort of given it away. What you're being asked to do, and this is our task first of all, is we're going to show that the sum of the first 100 natural numbers is 5,050. We're going to do it by not adding them all together. All right, so let's just scroll down a bit more before we get started. So let's create a bit more space. I'll leave Gauss on there so you can see him. All right, so how do we do it? Well, the first thing to do is to give this sum a name. Now, we call it S100. All right, well, I'm going to call it S100. And that simply means the sum of the first 100 natural numbers. And I'll explain, you'll see why I've set it out like this in a moment. So the sum is, of course, 1, add 2, add 3, add all the way up to 100, so 98, 99, 100. So how did he do it? Well, what we can do, and this is the trick, this is the essence of the problem. We're not bound to write the sum out in any particular way. We can write these numbers in any order we like. And one way we could do it is to write it backwards. So I'm going to write the sum again, but I'm going to write all of the terms backwards. So I'm going to start with 100, and then we're going to add each number, decreasing by 1 each time. So you can fill this in as well. Okay. Right. Now you could pause the video now and see if you can deduce what's special or what's interesting about writing the sums in this way. Why do we write it twice, forwards and backwards? All right, well, this is the key. If you haven't seen this, don't worry, but it is neat. Look at the summations vertically. So in other words, compare these values, and what do you notice in each case? Well, this is where you should be screaming at the screen now. What's actually happening? Well, if you add up vertically in each individual case, so here we get 101. 99 plus 2 is, of course, 101. 98 plus 3 is 101. And same thing again, just reversed round, 101, 101, and 101. So if you add the two sequences together, in each position, when you write them forwards and backwards, you get 101. So wouldn't it be great if we could solve this? Well, we're going to add each of these series vertically. Okay, so I'm going to add the two S100s together. Now, if I do that, like you would do with a simultaneous equation, if I add both equations together, on the left-hand side, I'm going to have two lots of S100. Okay. Now, on the right-hand side, we just have to consider how many numbers we've got. Well, that's staring at us. These are natural numbers, so they count for us how many terms we have. So we've got 100 terms. That's how many terms we have. Okay. But we've got 100 lots of 101. Okay. Because each of those sums is worth 101. So we have 100 101s by adding both series together. Okay, I hope that makes sense. Now, if we just simplify this a little bit, so this means that we have two lots of the sum of 100 terms is equal to 101 multiplied by 100, so just add two zeros on the end of it, and then divide by 2. So therefore, the sum of 100, so we're just halving the amount we've got, is 5,050. Isn't that amazing? So just to recap what we did, we wrote the sequence backwards, and then we wrote the series backwards, and we added each adjacent term, and we noticed that they were all 101. And we have 101 of these, we have 100 of these 101s when we combine the two series. All right, so now we've done the sum of the first 100 natural numbers. We're going to extend this idea for Gauss's sum. We'll call it Gauss's sum. And we're going to prove our formula. Now, this is an exam requirement. I'm going to stress this now. You will need to know how to do this for your examination. We're going to show that if you add up the first n natural numbers, concentrate, sir. If you add up the first n terms of an arithmetic series, you're going to get that formula. So just to remind you what an arithmetic sequence looks like, I'm just going to do it up here. Remember, an arithmetic sequence, the first term is A, and then we add a common difference each time until we get to a general term, which is, of course, A added to n subtract 1 multiplied by D, and so on and so on. Okay, so that's an arithmetic sequence. Now, the only difference, of course, is when we're considering a series, we're going to add all these terms together. Okay? Okay, so that would be the sum of the first n terms. So all of this, there'll be n of them. So let's do this. Now, in the question, or in the first statement where it's asking us to prove something, it says that the sum of the sequence is called Sn. So the capital S stands for sum, and the subscript how many terms you're summing. Okay, so that's what we're going to do. So we're going to call this sum Sn. So we're going to write that in here. All right. So Sn, and you see how I've partitioned it again, and we're going to write out each term of the sequence first of all. So the first term is, of course, A. Second term is A plus the common difference. Then A plus two lots of the common difference. Okay, and then we have the dot, dot, dot. Now then, For the first n terms, that means I've got to end with a added to n subtract 1 multiplied by d, which just fits in that box. Okay, because I've got to have n terms. And I just want to recap this because this is important. Remember that the first term has 0d. That means the second term, because we're adding a common difference, has to have 1d, which is the amount of d is always 1 less than the term you're in. The third term has 2d. Okay, so this must be over here the nth term, because there is n subtract 1 amount of d. The amount of d you have is always 1 less than the term you're in. I hope that's clear. So what we need to do is we need to work backwards and consider what would the term before the nth term be? Well, we know it's the n minus 1th term. Okay, that's clear. Okay, we know that, and we know the term before that would be the n minus 2th term. All right, and the amount of d we have is always 1 less than the term you're in. So let's just write down, okay, how much d do we have? Well, in this instance, if I have 1 less amount of d, that must be n minus 3d, which just fits in. And here we have n minus 2d. Okay, 1 less than the term you're in. All right. So when I'm writing it, I'm comparing these two numbers. Okay, so I'll just make it clear. The number in yellow here is 1 less than the number in green. The number in yellow is 1 less than the number in green. Okay, and so on and so on. Number in yellow, 1 less than the number in green. Now this is a series, so we need to add all of these together. So this is going to be plus, 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 plus dot, 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 plus some more. Okay. Now, when I've done this, what I strongly recommend you do, because I've given you quite a lot of scaffolding with this in terms of how it's presented, write it out again, maybe on a flashcard. Okay. And then every now and again, you can just try and practice in your own time. Okay. Now we're going to write out the series again, and this time we're going to use Gauss's trick. We're going to write it backwards. So we're going to start off with the nth term. So this is a added to n subtract 1 d, and then we reverse engineer it. So a plus n subtract 2 d, a plus n subtract 3 d. Okay, and then I'm going to start off on the far right over here. So this would be a plus d, and this would be a plus 2d. Okay, and then let's put the additions in all the way along. So this is the same summation, but written backwards, but it will give you exactly the same total. Doesn't matter which order you add the numbers up. Right, now that's the important work done. Now let's consider what Gauss did next. He noticed that vertically, when we did the sum of the first 100 numbers, remember he got 101 each time. If we look vertically, we should get the same amount each time. Now I'll just do a little aside here. Do we get the same amount each time? Let's just test the first two just to confirm it in case you're not convinced. So this is for term 1. Okay, so this is just an aside. This is not it's not officially part of the working out. If I add a plus n subtract 1 d, what do I get? Well, I'm going to get 2a added to n subtract 1 d. So I've basically just doubled the amount of a I've got. Right, how does that compare in the second column when I add up a plus d and a plus n minus 2d? Well, if we do that, we're going to have a plus d for the first part, and then we're going to add a plus n subtract 2d. Now, okay, let's collect like terms. Now, before we do that, it might be a good idea just to expand the bracket, just so you're absolutely convinced by this. Or I'll collect the a's together. So that's going to be 2a plus d plus dn subtract 2d. Okay? And when you do that, you can probably see now I've got a plus d here and a negative 2d here. I can combine those, and that's going to give me, oops, let's undo. That's going to give me 2a plus dn and then minus d. And we can factorize those two bits. So that's going to be n minus 1 d. So these seem to check out, don't they? We get the same expression. So when I add vertically in column 1, i.e. down this way, I get the 2a plus n minus 1d. And I also get 2a plus n minus 1d when I add vertically in this direction. So that's just a little aside. So I'm just going to box that off, because I just want to convince you that this argument is solid. Okay, it's not sorcery. It's not a trick. It does work. So if we're going to use Gauss's trick, okay, we're going to add vertically. All right, we're going to add vertically. Okay, we're going to add the two sums together, and then we can see, we've already done it, but we can see if we add these two together, we get 2a plus n minus 1d in every position. So let's just write that down officially. So adding each column, on the right-hand side, we will get 2sn, and then in position 1, we've already established we will get 2a added to n subtract 1d. So that's for position 1. Okay, position 2, we will get 2a added to n subtract 1d. And I think I've made my point. If we go all the way along, the final column, I mean, you can check it if you want to, but it's blatantly obvious because it's the same as the one we did here. Okay, these are just exactly the same calculation. You can see the a's are going to just combine to 2a plus n minus 1d. So I'm going to have 2a plus n subtract 1d, and I'm just going to put in all the additions. So that's column 2, that's column n. Add, dot, 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 add. Okay, so that's all the columns accounted for. Okay, so just add vertically. You can check them if you want to. There's the bell. Feel free to check them, but I guarantee you will get 2a plus n minus 1d in every single case, and it's very obvious in the nth term. Brilliant. Now, the question is, how many of these do we have? How many terms are there? Remember, this is the amount of rows in that diagram for the rectangle. Okay, well, we're summing the first n terms. It tells you in the question. And remember, this is the nth term. Okay, up there. All right, that's the nth term. So there are n of these. Okay, there are n of them. So I can write this as a multiplication instead. This is where it's getting exciting. So we now know that 2sn is simply n lots of, and I'm going to use big square brackets here, n lots of 2a added to n subtract 1 multiplied by d. Okay, and you can see the formula is going to pop out now. So all we have to do, there's the formula that we have to prove, divide both sides by 2, and we've got our result. So therefore, the sum of n terms is going to be n over 2 multiplied by 2a added to n subtract 1 multiplied by d. Okay, and that concludes the proof. All right, so now we've established the result. Let's have a look at some worked examples. So this is a variety of questions, how you can, well, things you might be confronted with about summing arithmetic series. So worked example 1, find the sum of the first 50 terms. Okay, the first 50 terms of the series that's given to us here. All right, first of all, let's just write down the formula again that we've just derived. So we already know, and this is given to us in the formula booklet as well, so don't worry. Oh, there's the bell. So you don't need to worry about memorizing this, but you do need to be fluent when using it. So it is a good idea to learn it in that sense. I would strongly encourage that you do. So that's the sum we've just derived. And the key thing here is we've got some, if we're going to use it, we've got some values that we need to substitute in. Now, if you notice, what do we need? Well, we need the n, we need an a, and we need a d. Okay, and there's another n there, obviously. Okay, so we need to know the values of a, n, and d if we're going to use this. Well, if we look at the question that we've been given, let's see what we can deduce. So the first 50 terms of the series, well, the first term is right here. Okay, so we can write down a is 12. N is obviously given to us. I'll just write that here because it's the first 50 terms. So we know we're summing over 50 terms. Now we just need to find the common difference. Well, remember the common difference. They've given us the first 4, so we can easily work out the common difference from that. So how many, or what we're adding between the 12 and the 15? Well, the common difference is clearly going to be 3, isn't it? We're adding 3 each time, if we think of this as a sequence, of course. All right. So we can state clearly now that the common difference D is, of course, 3. All right, so we've got all the information we need. We just substitute this information into the formula. So it's the sum of the first 50 terms, so it's S50. Okay, yes, just to reiterate, this value here, we're summing the first 50 terms. And let's sub in all the numbers. So that's going to equal n over 2. So that's going to be 50 over 2. And then we're multiplying that by 2 lots of a. So that's 2 multiplied by 20. 2 multiplied by 12. And then we're going to add n subtract 1. So that's 50 subtract 1 multiplied by D, which is the common difference. So this is just going to give us a value, isn't it? So let's just tidy this up a little bit. 50 over 2 is, of course, 25. And we're multiplying 25 by 2 multiplied by 12, which is 24, and plus 49 multiplied by 3. So yeah, get your calculators out to evaluate this. And when you do that, you should notice that the answer is 4,275. Okay, so we've completed the summation. Now, let's say you want to check your answer. Okay, can you do this on your calculator? Well, yes, you can. But it's going to introduce some notation we're not going to look at just yet. It's going to come up in a few lessons' time, but you can still do it. For the check, you'd need to know what the nth term rule is. Okay, so you would need the nth term rule, and then I'll show you how to do it on your calculator. Okay, so the nth term rule. Well, we know the common difference is 3. So we know it's 3n. All right, and so it's the 3 times table, and then we're adding 9 each time. Okay. All right. Now you can do that using the A and the D if you wanted to. So if you wanted to do it quickly, you notice that A is 12. D is, of course, 3. Okay, you sub them into the formula. So UN would be A added to N subtract 1 multiplied by D. So here I did it the old-fashioned way, using a translation of the 3 times table, but it doesn't matter which way you do it. So 12 add to 3n subtract 3, which is of course going to be 3n plus 9. Okay, now how do you check this on your calculator? Well, you can do what we call a summation on your calculator. Now, the notation is a little bit unusual. You may have seen it before. So on the class whiz, you would effectively type in this, and I'll show you how to do it in a second. So it's a big capital, well, it's a capital sigma, it's a Greek letter, and it will use the letter X here. Now, the number at the bottom is the term you're starting from, which is you're starting from the first term of the series, okay, the first term of the series, and you're summing the first 50 terms. So effectively, you're going from term 1 up to term 50. So just make a note of that. So what all that means is sum from term 1 to term 50. And then next to the summation, what are we summing? Well, we use the nth term rule. So in the bracket, and it uses the letter X, which is confusing, we would put 3x plus 9. Okay, and then you press equals, and it should give you the answer. So I'll just run through that on your on the class whiz with you. Okay, so on your class whiz, if I just erase some of this. So okay, and get rid of that as well. So on your class whiz, on your menu, you don't need your menu. Well, just select one. It doesn't matter. Okay. Does it let me tap it? Nope. That's better. Okay. No. Okay. What's going on with this? Sorry about that. More technical problems. Okay. So on your class whiz, the way to do a summation is to press the Shift key and then the X button. Okay. If you'll notice, if you press the Shift and the X button, which is just here, all right, you can see in yellow, it's the little summation. Now, that basically means it's going to add up the terms of a series for you. Okay. Now, once you've done that, if we put in the nth term rule, which is 3x plus 9, so I've typed in 3. To get the x, you need to use the alpha key, which is here, and you also need to use the X key, which is the right-hand bracket. All right, so if we do that, so it's going to be alpha X, so you get 3x and then plus 9. So that's the nth term rule for this this series. And then if we just go back and then we put in which terms we're summing. So we're going from the first term up to the 50th term. So it's the first term and then up to the 50th term. Okay, and then if you press equals, you get the answer, which is 4275. So that's a good way of checking. I mean, I know some of you are using photo math now, but if you want to use your calculator, that's a good way of checking it. Now, for example number 2, we're going to have to find the sum of a series. Now, this is where we get into slightly more problem-solving territory. We can't just, you'll see in a minute, we can't just sub directly into the formula. And the reason is if I just, again, just write out the formula so you're familiar with it. So the sum of n terms is obviously n over 2 multiplied by 2a added to n subtract 1 multiplied by the common difference d. Now, if you just look at the information we've been presented with in the question, what can we actually deduce? Well, we can see the first term, no problem. There it is, it's 7. So I'm just going to write that down. So the first term is 7, so that's A. Can we deduce the common difference? Well, yes, that's straightforward also. How do we get from 7 to 13? Well, of course, we're going to add 6. So we can see that the common difference is going to be 6. Great, so we've got that. But what about the n? How many terms are we summing over? Well, at the moment, we don't know. It just says we want to add up all the terms of the series from 7 up to 73, 73 being the last term of this series. But we don't know which term of the sequence we're in. So we need to figure this out. So there's a big question mark over n, okay? All right, so we need to figure out which term we're actually in. So, okay, going back to the information we've got, when we're summing a series, we're summing the first n terms of the series. So that means in this case, the nth term is 73. Okay. So i.e. un is equal to 73. Now we can use the general term of a sequence to find out which value, what the value of n is actually going to be, which term in the sequence the final term actually is. Okay, so we know that a plus n subtract 1 multiplied by d in this instance is 73. And we can sub in the a and the d. So if we do that, remember the a is 7, and then we're going to add n subtract 1 multiplied by the d, which is 6. And that's going to equal 73. Okay, let's just tidy this up so we can subtract 7 from both sides and multiply out the bracket. So 6n subtract 6 is, of course, 73 subtract 7, which is 66. We add 6 to both sides, so that's 72. So I get n equals 12. So that means that 73 is the 12th term of this series. So that's term number 12. If that's term number 1, it goes all the way up to 12. All right. Now you could have worked that out by writing out the whole series, but I wouldn't have recommended that. All right. Okay. Now we've got our n is 12. We can now apply the formula. So I'll just partition this. So let's use the formula. So Sn is going to equal n over 2 multiplied by 2a. Oh, I won't write it out again, actually. Let's sub in the numbers. Okay, I'll go back. Let's go back. So what is it? S12. Sum of the first 12 terms is equal to 12 over 2. Okay, that's n over 2 multiplied by 2 lots of a. So that's 2 multiplied by 7. Added to n subtract 1. Now n is 12, so that's 11. multiplied by the common difference, which is 6. All right, so a bit of number crunching. So 12 over 2 is, of course, 6. And we're multiplying that by 14 plus 66, which is, of course, 6 multiplied by 80. Okay, and that's actually quite nice. So 6 8s are 48, so the answer is 480. Okay, now then, at this point, I just want to introduce a new piece of information into this lesson. We found the sum of the series using the formula. Okay, now if you get a question where you're given the last term of the series, there's actually something else you can do. Okay, now remember what we said earlier. I'm just going to give you an alternative here. And it's worth knowing this because this can be very, very useful in certain situations. So an alternative would be to say, okay, this is the nth term. All right. So this is the nth term. And when you're summing n terms, it also means it's the last term of your series. Okay, it's the last term of your sum of n terms. Now, if that's the case, just consider the formula again. The formula says that the sum of n terms is n over 2. Now then, I'm going to split this up. Instead of writing 2a, I'm going to write it like this. It's going to be a plus another a, which is the 2a, plus n subtract 1 multiplied by d. Okay, now this is where it gets interesting. This bit, we've just mentioned this. This is the nth term or the last term of your series. So I can actually rewrite the formula in a really nice way. I can actually write it like this. So the sum of n terms is actually the same as n over 2 multiplied by a plus, now I'm going to use capital L for this. Okay, and I'm just going to make a note of that, where big capital L is the last term. Of the series. So how does this help us? Well, it means we can answer this question probably a lot quicker, and it would actually be more useful in other situations where they tell you how many terms are in the series. So let's just do a check. So the sum of 12, the first 12 terms, is of course going to be 12 over 2 multiplied by a, which is of course 7. And if you add the last term, which is 73, you do of course get 6 multiplied by 80 again, which is of course 480. Now, I've said this is a bit of extra information. It's not strictly the case, because if you remember right back at the beginning, we actually worked out the sum of the series using both the first term and the last term. All right, that's how we did it. We added this number 7 to the 73. We multiplied it by how many terms there are in the series. Okay, so 7 plus 73, first and last. We now know there are 12 terms in the series, and then we divided the answer by 2. So it's just the form that we looked at right at the beginning. Okay, so it's a valid way of writing the summation, and it can be very, very useful. Okay, so for worked example 3, we're asked to find a sum or the least number of terms for the sum to exceed 1,000. Right. So let's write this mathematically, okay? What are we being asked to find? We want the sum. So we're finding the number of terms. So when it says number of terms, it seems to suggest we're finding a value for n. And we want this sum to exceed 1,000. So in other words, we want this Sn to be greater than 1,000. All right. And always have in the back of your mind that these n values, these are natural numbers because they represent terms of a sequence or series. Right. So that's what we want to find. We want to find Sn and we want to set it greater than 1,000. All right. Well, let's write this out using the formula. Now, we don't have the last term here, so we'd be well advised to use the original form for the sum. So that means that n over 2 multiplied by 2a added to n subtract 1 multiplied by d. When does that exceed 1,000, or when is it greater than 1,000? All right. Now we know n is what we're trying to find. So what are the other values that we need in order to set up an equation for n, or an inequation for n in this case? Well, we need to find a, okay, and we need to find d, and everything else will be, so the equation will be in terms of n, inequation or inequality. So let's write down what a is. That's the easiest one, isn't it? So it's the first term, which is 3. Okay, right there, given to us. Okay, and we need the common difference. Common difference, so how do we get from 3 to the next term, which is 8, so it must be 5. We're adding 5, so it's a positive 5 there. All right, so we have everything we need. So we're going to substitute these two values into this inequality, and let's see what happens. Okay. So we have n over 2 multiplied by 2a, so that's 2 multiplied by 3, added to n subtract 1 multiplied by d. Well, okay, so that's n subtract 1 multiplied by 5, and this has to exceed 1,000. Okay. What can we do here? Well, let's tidy up inside the bracket first of all. So n over 2, then we have 2 multiplied by 3, which is 6. Multiply 3 by 5 inside that smaller bracket. It's 5n subtract 5. Close the big bracket, and that's greater than 1,000. It's up to you how you proceed. We can do a bit more tidying up inside the bracket. Okay. Okay, so let's do that. So n over 2. 6 subtract 5 is, of course, 1. So we have 1 plus 5n. Close your big bracket. Is greater than 1,000. Let's multiply across by 2. So we have n, and then 1 plus 5n. Close your square bracket is greater than 2,000 because we're doubling everything. And let's multiply out the bracket now. So we have n added to 5n squared is greater than 2,000. Right, we have a quadratic inequality. Let's get everything onto one side of the quadratic inequality. So 5n squared plus n subtract 2,000 is greater than 0. Now, you may recognize this result. We got this in the warm-up question 3, I believe. Okay, and we solved this. And remember, we got 2 solutions. We solved this on our calculators. And we got n equal to, now just refresh my memory, 19.9. Okay, or n equal to a negative solution, minus 20.5. 19.1. Now that was when we were solving an equation, a quadratic equation. This is an inequality or an inequation. So we do have values of n, but remember I said to you at the beginning, you should always have at the back of your mind that these values of n that we're talking about here and here and here, in the context of a sequences and series question, these have to be natural numbers. Okay, so we need to use a bit of reasoning to answer this question, because clearly we can't just leave it like this. So it says the least number of terms required for the sum to exceed 1,000. Well, if we're talking about natural numbers, and which we did right at the start of the course, we can straight away look at this and disregard this answer here, okay, because it's negative. So that can't be one of our answers. You can't have a negative term. Well, you can have a negative term, but you can't have a negative position in a series. So let's solve the inequality, and then we can hopefully move forward with this. So this is an inequality, and we've just found what the roots of the inequality are. So these two values here represent the roots of the inequality. So these two values I'm talking about. All right, so let's just draw the quadratic. Now, also please bear in mind that the quadratic has a positive x squared coefficient here. Okay, that's a positive number, so we know it's a U-shaped graph. So I'm just going to indicate, this is for your notes, of course, a revision document, so you need to remember to do this. So sketch the quadratic. It's a U shape. You don't need the y-intercept. Okay. Now, in this case, this is your n-axis. We're talking about n in this case. And the two values that we discovered, well, we had the one we've disregarded, but we'll mark it on anyway. Okay, and the other one, 19.9. All right. The inequality tells us that this quadratic has to be positive. Now, we've already disregarded the negative part, so that's no good. So we're only really focusing on this part. Now, obviously, the graph is positive when, sorry, beg your pardon, the solution will occur when n is greater than 19.9, because that's when the quadratic graph is above the x-axis. All right, so to solve the inequality, first of all, we can say that n has to be greater than 19.9. Okay? Because we've disregarded the negative 20. It can't be positive because we're talking about natural numbers. But 19.9 isn't a natural number either. So we have to find a natural number that is greater than 19.9. Well, the only possible conclusion we could draw from this is if n equals 20. Okay? That has to be the answer. Okay, and if you want to, you can check this on your calculator. So if you want to use the summation on the class whiz, you can work out the nth term rule and plug in so it would be x equals 1 up to 20, and you should get a value that is greater than 1,000. If you plug in, so if I just undo that bit, if you did it up to 19 only, you would find that the summation, the value would actually be less than 1,000. Okay, if this is correct. All right, now our fourth and final example for today, we're given some interesting information here. We're told this is an increasing arithmetic sequence. Okay, so they've actually bothered to tell us that this is an increasing arithmetic sequence. So that means it has a common difference and the values of each term are increasing. okay? And this is absolutely crucial that you pay attention to this. We're given the second, third, and fourth terms, okay? Not the first three, okay? The second, third, and fourth terms. Now, that looks like this is going to be important. So that's the second term. That's the third term. And this is the fourth term. And we have to show that the sum of n terms of this sequence is a square number. Well, we've confronted questions like this before, haven't we? We need to find the sum of n terms. So again, let's write down what we know. We know what the sum of n terms is. It's n over 2 multiplied by 2 lots of the first term plus n minus 1 multiplied by the common difference. So what is absolutely clear is that I don't need to know n because we're finding the sum of n terms, okay? So we're summing over n terms, so that n is going to remain as n. What we need to find is a and the common difference, okay? Now then, a, remember, is the first term. We don't actually have a representative in terms of k for the first term. We only have the second, third, and fourth terms, but we can find d using this, and we've used this technique a few times already. So remember, to get from the second to the third term, I'm adding the common difference. To get from the third to the fourth term, I'm also adding the same common difference. Okay, so first job, let's find d. Okay, so I'm going to make that note again. So if I subtract the third term from the fourth term, that will give me d, and it's exactly the same as subtracting the second term from the third term. Both of these are equal to the common difference. So that's where I get my equation from. So let's do this. So fourth term, subtract the third term. So that's k squared plus 3 for the fourth term. Subtract 4k, which is the third term, must be equal to 4k, which is the third term, subtract the whole of k plus 7, which is the second term. So we just tidy this up and solve this quadratic. All right, so k squared, add 3, subtract 4k is equal to 4k, subtract k, subtract 7. Let's get everything onto one side and collect like terms. K squared. Now, so here we've got negative 4k. I'm going to have to subtract the 4k here and then add the k here. Let's deal with the k's first. So that will be negative 7k. And then we have the positive 3 here, and I'm going to have to add 7 to both sides. All right, so that's reasonably straightforward. It looks like this will factorize too. So that's going to be plus 10 is equal to 0. Yes, and this factorizes really nicely. So we have k, 2 and 5, both negative. So either k equals 2 or k equals 5. Right, now that we've got that, we've got two values of k here. How does this help us? Well, if we have two possible values of k, this is going to generate two different sequences, isn't it? So we need to establish what's going on with each sequence. So let's have a look at when k equals. So when k equals 2, let's see what happens. Well, my sequence is going to be k plus 7. All right. So I'm going to get, when k equals 2, we get k plus 2, which is 7. Sorry, I beg your pardon. K plus 7, which is 9. Then we have 4k. Now 4 times k, so that's 2 4s are 8. So I'm just substituting in k equals 2 into all this. Okay. Remember, this is the second, third, and fourth terms. And then I have k squared plus 3. So k squared is 4, add 3 is 7. Okay, and then I would also have the first term here, which I haven't been given. Now, if you'll notice, the values are getting smaller. It's decreasing by 1 each time. So my common difference in this case would be -1. And this is a decreasing arithmetic sequence. All right, now why is that important? Well, this means that this is not the value of k that we want, because it states in the question that it's an increasing arithmetic sequence. So this is not the value of k that we want. So it must be that when k equals 5, this must be the one that we need. So let's just test it just to make sure. So when k equals 5, what sequence do we get this time? All right, well, we have 5 plus 7, which is, of course, 12 for our second term. Don't know what the first term is. 4 times k, so that's 4 times 5, which is 20, and which is increasing. This looks good. And k squared, which is 25, plus 3, which is going to be 28, which is an increasing sequence. Brilliant. Okay, so this is an increasing sequence, which is what we wanted. So this is the correct value of k that we're going to use. All right. Let's just partition the board. Now then, what do we have to do with this? Well, we have to show that the sum of n terms of this sequence is a square number, but we need to write out the sequence properly. Okay, so we need the first term. Now, the first term which is, of course, a. Now, we're going to have to subtract the common difference from 12, which was the second term. Now, common difference, of course, as you can see from here, is going to be positive 8. So I have to subtract 8 from 12, so that's going to give me 4. Okay. So therefore, when k equals 5, we get this sequence. I'll write it in a different color. So we get 4, 12, 20, 28, and so on and so on. Okay, and now we have to find the sum of n terms. So now find Sn. Okay, so just jot down the key ingredients here. So we know that A is 4 and the common difference is 8. So K is 4, a common difference of 8. Just indicate it on here again. Okay, let's sub those into the summation formula. Nearly there. So Sn is equal to n over 2. Okay, it says show that it's a square number. Well, okay, well, let's not worry too much about it. Let's just keep going through the process. Have trust in the process, and hopefully the result will fall out at the end. So multiply that by 2a, so that's going to be 2 multiplied by 4, added to n subtract 1, multiplied by the common difference of 8. Okay. All right, so we have n over 2. 2 multiplied by 4, which is 8. And then if I expand the bracket, that's going to be 8n subtract 8. Now the 8's will cancel out. So this is going to be n over 2 multiplied by 8n. Okay. Now this is going to equal, so we're going to have n squared, 8 over 2 is 4. So this is going to be 4n squared. Now, how do I know this is a square number? Well, it's quite easy. Notice that 4 is a square number and n squared is a square number. So it's simply just 2n all squared. So this is a square number. Okay, and if you're interested, go and check question 2 of the warm-up and see if you can see a similar result there. Okay, thank you very much.